Hello everybody. Hope I'm live. I'm not sure though. Um yeah, today we're going to read the zoo we're going to start reading the circuits thread. So this is a very popular series of you cannot call it research papers, but they're basically research papers. They were published by OpenAI initially. By Chris Sala. He is like I think he's the primary one among all this. And it is very popular. So this is all about interpretability, and these are basically they are research papers. So I want to read them, and here we start. In fact, there is a second part to this circuits thread, which is made by Anthropic, again by Krisala, and one among that paper is the monosemanticity paper, which we read once. So this is actually honestly not our introduction to circuits, but we are being introduced to circuits. Right, before we start, just ensuring we are live. Yes, sir. Now, a warning. I'm going to like close my dark reader for a second so that I can read that part. Alright, that's right. Sorry. By studying the connections between neurons, we can find meaningful algorithm in weight of neural networks. Windows car bodies. 3 speculative claims. Claim 1 feature. Okay, I think we will realize what the word feature means. Oh, polysematic neurons. Okay, you are important. Claim 2 circuits. Okay, you're making 3 claims, huh? That's the whole paper. That's what the whole paper is about. Claim 3 okay, universality. Analogous features and circuits form across model. Okay, analogous features and circuits form across models and tasks. Oh, and they are using what do you call it? Like many image models for learning this, primarily because the features are easier to detect, right? Like compared to a text. So forward that. Yeah, so I want to read this, and let's read this. So let's put our black glasses on, and I want to start noting this down. So AI not, I mean, no, I'm reading papers, right? Reading research papers. And we have this thing on. That's monosoma. Oh, okay. So we are going, that is paper number 26. Circuits and introduction. So I'll have a main dot marked on, right? So zoom in an introduction to circuits. So I'll also do this. Okay. So I'll also write apply. So okay. By studying the connection between neurons, we can find meaningful algorithms in the weight of neural networks. I'm just going to try this here. This looks like the key point in this paper. Okay, cool. Kursala, Nick, Ludwig Schmitz. Okay. Published on March 2020. This is also a paper. Oh no, that's a this link. This article is a part of the circuit thread, An experimental format collection of invited short articles and critical commentary delving to the inner workings of neural networks. Yes, there's a previous article, I know that. Oh, this is it. Okay, I think we'll start reading from here. Okay, in the meaningful narrative of deep learning, each neuron builds progressively more abstract, meaningful features by compassing features in the preceding layer. In the recent years, there's been skepticism of this view, but what happens if you take it really seriously? Inception V1 is a classic vision model with around 10,000 unique neurons. A large number, but still on a scale that a group effort could attack. What if you simply go through the model neuron by neuron, trying to understand each one and the connections between them? The circuits collaboration aim to find out. Okay. The natural route of obligation for investigating circuits seems to be on short papers on individual circuits or small families of features. Compared to normal machine learning papers, these are small and unusual topics for a paper. To facilitate exploration of this direction, history is inviting thread of short articles on circuits interspaced with critical commentary by experts in adjacent fields. The threads will be a living document with new articles added over time. Organized on an open Slack channel, content in the thread should be seen as an early stage of exploratory research, and I really wish this continued. Articles and comments are present below in chronological order. Okay, this is a zoom in. Does it make sense to treat individual neurons and the connection between them as a severe subject of study? Okay, so this kind of answers if the whole study of neuron, the whole study about circuits is necessary. The essay proposes three claims, which, if true, might justify serious inquiry into them. The existence of meaningful features, the existence of meaningful circuits between features, and the universality. Okay, I'm very silent to read the word universality. And the universality of those features and circuits. It also discusses historical successes of science, zooming in whether we should be concerned about this research being qualitative and approaches to rigorous investigation. Okay. An overview of early vision in Inception V1. So maybe we have to read the Inception V1 paper before reading this question mark. I don't know. Maybe we don't. I don't know. An overview of the neurons in the first 5 layers of Inception V1 organized into taxonomy of neuron groups. This article sets the stage for future deep dives into particular aspects of early vision. Curve detectors. Early vision model we have explored in detail contain neurons which detects curves. That's interesting. Curve detectors is the first in the series of 3 articles exploring this neuron family in detail. Naturally occurring equivariance in neural networks. Neural networks naturally learn many transformed copies of the same features, connected by symmetric weights. Okay. High-low frequency detectors, a family of early vision neurons reacting to directional transition from low to high spatial frequency. Curve circuits. We reverse engineer a non-trivial learned algorithm from the weights of a neural network and use its core idea to craft an artificial neural network from scratch that re-implements it. I missed it. We reverse engineer a non-trivial learned algorithm from the weights of a neural network and use a core idea to craft an artificial neural network from scratch that re-implements it. Okay. Visualizing weight. We present a technique for visualizing context, visualizing and understanding neural network weights. Okay. When a neural network layer is divided into multiple branches, neurons self-organize into coherent grouping. Weights in the final layer of common visual model appear to be horizontal bands. We investigate how and why. Okay, not anymore. They intended to be earlier stage than a full digital paper and allow for more fluid publishing, feedback, and discussion. We also hope that they will allow for wider participation. Think of it as a cross between Twitter thread and academic workshop, a book of collected essays. Alright, so let's start reading the first book, Introduction to Circuits. Many important transition points. So, this is circuits thread 1. Many important transition points in history of science have been moments where science zoomed in. At these points, we develop a visualization or a tool that allows us to see the world in a new level of detail, and a new field of science develops to study the world through its lens. For example, microscopes let us see cells, leading to cellular biology. Science zoomed in. Several techniques, including X-ray crystallography, let us see DNA, leading to the molecular revolution. Science zoomed in. Atomic theory, subatomic particles, neuroscience. Science zoomed in. These transitions weren't just a change in precision. They were qualitative changes in what the object of scientific inquiry are. These transitions weren't just a change in position. They were qualitative changes in what the object of scientific inquiry are. I don't understand what that means. I'll skip it. I get the general idea though. For example, cellular biology isn't just more careful zoology. Oh, okay. Yeah. It's a new kind of inquiry that dramatically shifts what we can understand. Micrographia. Hooks micrographia reveals the rich microscopic world as seen through a microscope in the initial discovery of cells. The famous example of the phenomenon happened at a very large scale, but it can also be the more modest shift of a small research community realizing they can now study that topic in finer grained level of detail. Okay. Just as early microscopy, just as the early microscope hinted at the new world of cells and microorganisms, visualization of artificial neural networks have revealed tantalizing hints at the glimpse of rich world within our model. Okay, this has led to wonder: is it possible that the deep learning is at a similar, albeit more modest transition point? Okay. Hmm. Okay. This is an Android paper, right? Yep, sure. Linux kernel dataset. What is that? Git commit log with detailed information. Commit hash. File name. Subject. Interesting. Hmm. Visualizing understanding RNNs. Okay. Visualizing higher layer features of deep network. It's unfortunate that I can't go to this article link by pressing the link. Feature visualization, Krasala. Deep inside the CNN. Deep neural networks are easily fooled. High confidence prediction for unrecognizable images. Inceptionism. Going deeper into neural network. Play and play. Generative networks. Visualizing. Okay. That's a lot of literature for interpretability, man. And I have to read all of them. That's okay. I will. This has led us to wonder, is it possible? Okay. Most of the work on interpretability. I mean, I kind of want to like save all this kind of. Man, sad. Oh, wait. Oh, I got it. Okay, so I wasn't expecting that. This has led us to wonder, is it possible deep learning is an okay. Most of interpretability aim to give a simple explanation of an entire neural network behavior. But what if instead take an approach inspired by neuroscience or cellular biology, an approach of zooming in? What if we treated individual neurons, even individual weights, as being worthy of serious investigation? Okay. What if we were willing to spend thousands of hours tracing through every neuron and its connections? What kind of picture of neural network would emerge? Okay. In contrast to the typical picture of neural network as a black box, we have been surprised how approachable the network is on this scale. Really? Hmm. Introduction. No, that's not true. Most interoperability research focus on focuses on understanding what a neural network as a whole is trying to do. In these papers, the researchers to understand the working of individual neurons in a neural network by spending Like I have to like, clearly specify time tracing through the neurons. And it also has this thing. Okay. Not only do neurons seem understandable, even one that initially seemed unscrutable, but these circuits of connections between them seem to be meaningful algorithms corresponding to facts about the world. You can watch a circle detector be assembled from curves. You can see a dog head, you can see a dog head be assembled from eye, snout, fur, and tongue. You can observe how a car is composed from wheels and windows. You can even find circuits implementing simple logic, cases where the neural network implements and or XOR our higher level visual features. Is it? The introductory essay offers a high-level overview of our thinking and some of the world principles that I found useful in this line of research. In future articles, we and our collaborators will publish detailed exploration of the inner world. But the truth is that we have only scratched the surface of understanding a single vision model. If this question resonates with you, you are welcome to join us and the collaborators in the circuits projects, an open scientific collaboration hosted on Distill Slack. Is there something there? Hmm. The speculative claims. Okay, give me a second here. All right. Three speculative claims. One of the earliest articulations of something approaching modern cell theory was three claims of Theodore Schwann's, who you may know for Schwann's cells. Schwann's claims about cells. The cells is the unit of a structure, physiology, and organization of living things. Okay. As the cell retains a dual existence as a distinct entity and a building block in the construction of organism. Cell forms. Cell forms. Cells form by free cell formation, similar to the formation of crystals. The first of these claims are likely familiar, possessing in modern cellular theory. The third is likely not familiar since it turned out to be horribly wrong. We believe there's a lot of value in articulating a strong version of something one may believe to be true, even if it might be false, like someone's third claim. Yeah, like Dalton's atomic theory, right? In the spirit, we offer three claims about our neural networks. These are intended to be both empirical claims about the new nature of neural network and also as normative claims about how it's useful to understand them. Features, circuits, and universality. Claim 1 features. Claim 2 circuits. Claim 3 interpretability. Okay, you are trained on this data set. I get it. Features are the fundamental events of neural networks. They correspond to directions. These features can be rigorously studied and understood. Features are connected by weights, forming circuits. Okay. So circuits are higher level features. These circuits can also be rigorously studied and understood. Analogous features and circuits form across models and tasks. By direction, we mean a linear combination of a neuron in a layer. You can think of this as a direction vector in the vector space of the activation of a neuron in a given layer. Often we find it most helpful to talk about individual neurons, but we will see that there are in some cases where other combinations are a more useful way to analyze networks, especially where neurons are polysemantic. Alright, claim few circuits. A circuit is a computational subgraph of a neural network. It consists of a set of features and the weighted edge that goes between them in the original networks. Often, we study quite small circuits, say with less than 1,000 features, but they can also be much larger. Okay. Oh, it's not actual interpretability. You're not trying. Okay, my bad. Okay. These claims are okay. We believe these claims are important to be considered. Important to consider because if true, they could form the basis of a new zoomed in field of interpretability. In the following sections, we will discuss each one individually and present some of the evidence that has led us to believe they might be true. Features are the fundamental units of neural networks. They correspond to directions. In a vector space. We claim one features. Neural network consists of meaningful understandable features. All layers contain features like edge and Curve detectors, while ATLS contain have features like floppy ear detectors or wheel detectors. Okay. The community is divided on on whether this is true. Really. While many researchers treat the existence of meaningful neurons as almost a trivial fact, there are even small literature studying them. And I feel like I have to read all of these to actually read the paper, read this paper. But then I feel like it just becomes never ending. Alright. Many others are deeply skeptical and believe that past cases of neurons that seem to track meaningful latent variable were mistaken. Okay. Nevertheless, thousands of hours of studying individual neurons have led us to believe the typical case is that a neuron, or in some cases, other directions in the vector space of neuron activations are understandable. Understandable. Of course, being understandable doesn't mean being simple or easily understandable. Many neurons are initially mysterious and don't follow our prior guesses of what features might exist. However, our experience is that there's usually a simple explanation behind these neurons. Hmm. And that they are actually doing something quite natural. For example, we are initially confused by high low frequency detectors, but in retrospect, they are simple and elegant. This introductory essay will only give an overview about a couple of examples we think are illustrative, but it will be followed by both deep dives carefully characterizing individual features and broad overviews, stretching out all the features we understand to exist. We will take our examples from Inception V1 for now, but believe these forms hold generally and will discuss other models in the final section of universality. Regardless of whether we are correct or mistaken about meaningful features, we believe this is an important question for the community to resolve. We hope that introducing several specific, carefully explored examples of seemingly understandable features will help advance this dialogue. Okay. Example 1, curve detectors. Curve detecting neurons can be found in every non-trivial vision model we have carefully examined. These units are interesting because they straddle the boundary between features the community broadly agrees exist, that is, X edge detectors, and features for which there is significant skepticism. ES, automatics, and face. Okay. Okay, I am between them. So, edge detectors does exist. Nobody knows if ear detectors exist. Curve detectors stand somewhere between them. We will focus on curve detectors in layer mixed 3B, an early layer of inception. These units also responded to curved lines and boundaries with radius of around 60 pixels. They are also slightly additionally excited by perpendicular lines along the boundary of the curve and prefer two sides of the curve to be different colors. Curve detectors are found in family of units, with each member of the family detecting the same curve features in a different orientation. Together, they jointly span the full range of orientation. Families of units. Each family of the member detecting the same curve feature in different orientation. Okay. It's important to distinguish curve detectors from other units which may seem superficially similar. In particular, there are many units which use curves to detect curved subcomponents. These are also units which respond to curve-related shapes like line or sharp corners. We do not consider these units to be curve detectors. Hmm. Okay. We often see 7 arguments outlined below. It's worth noting that none of these arguments are curve specific. They are useful general toolkit for testing the understanding of features as well. Several of these argument dataset examples, synthetic examples, and tuning curves are classic methods from visual neuroscience. The last 2 arguments are based on circuits, which we will discuss on next section. Feature visualization, optimizing the input to cause curve detect justify reliably produces curves. This establishes a causal link, a causal link, since everything in the resulting image was added to cause the neuron to fire more. Dataset examples. The image examples that cause the neuron to strongly fire are reliably caused in the expected orientation. Synthetic examples. Curve detectors. We take dataset examples that cause a neuron to fire and rotate them. They gradually stop firing, and the curve detectors in the next orientation begin firing. Hmm. Nice. Hmm. The downstream client of a curve detector are the feature that naturally involve curves. Curve detectors are used by these clients in an expected manner. Handwritten circuits. Based on our understanding of how curve detectors are implemented, we can do a clean room re-implementation, hand settings, all waits to re-implement our curve detection. These weights are understandable curve detection algorithm and significantly mimic the original curve detectors. The above argument don't fully exclude the possibility that some rare secondary case where curve detectors fare for different kind of stimulus, but they do seem to establish that curves cause neurons to fire. Each unit corresponds to a curve at a different angular orientation. If there are other stimuli that cause the fire, those stimuli are rare or cause weaker activations. More generally, these arguments seem to mean that the evidently standards we understand to be used in neuroscience, which has established traditions and institutional knowledge of how to evaluate such claims. Of all these arguments, hmm, okay, cool. So curve detectors, right? They exist. Okay. Okay, I'm going to stop for a while, take a rest and come back. Right? Give me a second. All right. So I think all is fine. Yeah, let's continue reading, right? So we were reading about circuits and features. So what is the difference between circuits and features, right? That's an important question. What is the difference between circuits and features in the interpretability research? Circuits and features are distinct yet interconnected concepts. Representation or concept that a model has learned to recognize and represent internally. These can range from low-level features like edge or textures to high-level features like objects. Features are typically associated with specific neurons or activation in a network. Features are often hierarchical, meaning building from simple patterns. Circuits refer to mechanisms or pathway by which features are computed and combined across multiple neurons and layers in a network. They are essentially the wiring of an interconnection between neurons that implements specific computation or decision-making process. Features the pathway combines edge and texture features to detect cat faces. Features are building blocks of circuits. Circuits provide the computational graph or mechanism through which features interact to produce behavior. A circuit for detecting dark space might combine features like dark ears and dark eyes, which are themselves learned by the circuits at lower layers. Features are representations or concepts the model has learned to recognize and represent internally. These can range from low-level features to high-level ideas. Okay, let's go and paste these guys here. They typically are made with one or a few number of neurons. Okay. Okay. So that is features and circuits. All right. High low frequency detectors. Frequency detectors are an intuitive type of feature. The kind of feature one might guess exists in your network given a priori. Curve detectors. Oh, sorry. Given that they are present, it's not surprising that we understand them. It's not surprising that we can understand them. But what about features that aren't intuitive? How can you also understand them? We believe so. High low frequency detectors are an example of a less intuitive type of feature. We find, here I'll give examples. I will claim that curve detection features exist in neural networks. They are very intuitive to find and study. Oh, I can. Oh, I can also do this, huh? Oh, that's so cool. Okay, that's very helpful. High Lala detectors. Okay. There are also features that are less intuitive. Okay. We find them in early vision, and once you understand what they're doing, they're quite simple. They look for low frequency patterns on one side of the receptor field and high frequency patterns on the other side. Okay. Like curve detectors, high low frequency detectors.